All right, so we're going to look at the unit circle together. And talking about the unit circle usually needs to start with talking about angles. We build the unit circle out of all of these angles because the unit circle helps us build our trig functions, sine, cosine, tangent, and our new friends, secant, cosecant, and cotangent. And so those 6 functions all depend on the unit circle. And so we build this out of all of these reference angles. And so it's important to define a few terms. Yesterday we talked about positive and negative coterminal angles, so angles that both have their initial side on the x-axis and their terminal side lands in the same place, regardless of which direction they went around or which or how many times they went around the circle. So an angle in standard position, all the angles we work with during this unit, an angle will be angles in standard position. So standard position has its initial side on the x-axis. So its initial side will land on the x-axis and the positive x-axis, I should say, the positive x-axis. And rotates around the origin, so our point of rotation will be around the origin. I'll give us a nice point there, until it reaches its terminal side. So when you sketch an angle, the initial side is on that positive x-axis, if it's in standard position. And then say my angle starts there and goes around in the positive direction, that is counterclockwise, until it reaches an angle of 2 pi over 3. So this angle here, represented by the arrow, is 2 pi over 3. And so that is the number of radians in between these 2 sides creating the angle. All right, so you may also know the positive coterminal angle would be greater than 2 pi, because we would add 2 pi to 2 pi over 3 if we wanted to find the positive coterminal angle, and we'll look at that really quick just to remind ourselves. Now 2 pi in terms of pi over 3s will be 6 pi over 3, so a positive coterminal angle would be 8 pi over 3, and so that angle would go around to 2 pi over 3 and then around, so around to 2 pi over 3 and then around an entire 2 pi to reach that same terminal side, a coterminal angle. A negative coterminal angle would require us to subtract 2 pi. So I'll subtract 6 pi over 3, and that is negative 4 pi over 3. Now we know positive angles start at that positive x-axis, the initial side, and travel counterclockwise. So we'll start in the same place and travel 4 pi over 3 clockwise to go in the negative direction. So that is negative 4 pi over 3, and I sketch the arrow to represent the angle, and it starts at the positive x-axis, that is the initial side, and ends at the terminal side, that is wherever the angle lands. Okay, so that's a quick example of a positive coterminal and a negative coterminal. All right, so reference angles are going to use these pieces of vocabulary that we've been using, and I'm not necessarily going to do all of these, and I honestly prefer to work in radians. Radians are your new best friend. We are going to do everything in radians. So we're starting with some of both, just so that we can connect what we know and what we're comfortable with in degrees to radians. But I promise it gets easier when you get comfortable with radians. So a reference angle, any angle, for example, this angle theta is roughly 2 pi over 3, looks a lot like the angle we just sketched, maybe also a 3 pi over 4, hard to tell. Everything's not exactly to scale. But just for example, this angle theta in blue has a reference angle between the terminal side and the nearest side of the x-axis. So I could also drop a perpendicular and create a triangle, and that is a reference angle. Now, if I was working with another example, say 150 degrees, I will sketch that angle. 150 degrees is only 30 degrees shy of 180, which I know is a straight line. So if my initial side is the positive x-axis and my terminal side is 150 degrees around, I'm going to rotate this terminal side. There's 90 degrees. There's 90, and then 45 more. Doesn't want to line up perfectly nicely. And here I reach 150 degrees. That is 30 degrees shy of 180 degrees. And I'm going to make this line up a little bit nicer so that it just makes all of our brains happier. There we go. Now they should be perfect. There we go. So our 150 degree angle is right here. Here's our 150 degree angle. The reference angle for this angle will be that 30 degrees shy. Here's our reference angle. It creates a triangle with the nearest positive x-axis. All right, let's look at another one, and let's look at one in radians. What if I look at 5 pi over 3? Now, I know pi over 3 is 60 degrees, so I'm going to go 60 degrees 5 times. 60 degrees lands in the first quadrant. Here's another 60 degrees. So there's a 60, there's another 60, there's another 60, because I know 60 times 3 gives me 180. Another 60 degrees would be 4 pi over 3, and 180 plus 60 puts me at 240. And then another pi over 3 puts me at 5 pi over 3. That's another 60 degrees, and all my drawings are not perfect. This would have been a little more like that. Okay, so here is our 5 pi over 3 angle. Notice it's easy to find a coterminal angle coming down from that positive x-axis. It so happens that the coterminal angle here, the negative coterminal angle, the closest one, is also our reference angle. So if I connect my angle, the terminal side of my angle, to the nearest x-axis, in this case the positive x-axis, the angle it creates is the reference angle. That also happens to be the coterminal angle here. So it is easy to find it. There's only 1 pi over 3 left to make the whole rotation. The whole rotation would be 2 pi. So the whole rotation would be 2 pi. And when we go 5 pi over 3, there's only 1 pi over 3 left to get to 6 pi over 3, which would simplify to 2 pi. So this reference angle is pi over 3. All right. Remember, negative angles just affect the direction that you go from the positive x-axis, that initial side, whether you go clockwise, which is the negative direction, or counterclockwise, the positive direction. So let's start talking about the unit circle itself. We're going to build our unit circle out of reference angles. And the purpose of the unit circle is to help us define our 6 functions and the values of them. So we know the sine is in reference to our unit circle. We know sine is opposite over hypotenuse. And our handy-dandy little triangle here lets us see opposite of theta would be this side of the triangle. That is the y direction. That is the y height of our point on the unit circle. And so y over 1 is just 1. Since 1 is the hypotenuse, that is the radius of the circle, and at any point, that's our definition of a circle, all points equidistant from a given center point. And so we see also that the x value, or the x distance from the origin, is our cosine value, because cosine is adjacent over hypotenuse. The adjacent side to theta is the side with length x, and x over 1 is just x. We know tangent is opposite over adjacent. So the opposite side here is y, and the adjacent side here is x. So notice we also can derive our first trig identity. This is a sneak peek at next unit. Tangent is equal to sine theta over cosine theta. Tangent of theta is equal to sine theta over cosine theta. Go ahead and start putting that into your brain, because it is the first and one of the most important trig identities. And we'll talk more about what specifically an identity is next unit, okay? Cosecant is the reciprocal function of sine. I always remember that c's goes with s's, so sine goes with cosecant, and cosine goes with secant. So the reciprocal of y over 1, is 1 over y, and so our cosecant function will be 1 over y. Our secant function similarly will be 1 over x, and the cotangent function will be x over y. And similarly, the reciprocal of sine over cosine is cosine over sine. So cotangent is cosine over sine. For now, just focus on sine over cosine. Tangent is sine over cosine. That will always, always, always be true, no matter what theta is. So now that we have this foundation of reference angles and how we can see sine, cosine, tangent, cosecant, secant, and cotangent in the unit circle, we're going to use this to label our unit circle, all right? So connecting these pieces, the coordinates of P, this point P can be written as cosine theta, sine theta. Since x values are equal to cosine and y values are equal to sine, the points of P are written as cosine, comma, sine. All right. So the unit circle, this is a little similar to what we had above. Sine is, and I'll go ahead and rewrite this so we have it. Sine is y, cosine is x, tangent is y over x, cotangent is x over y, secant is 1 over x, and cosecant is 1 over y, and our coordinates are cosine theta, comma, sine theta. So the unit circle is frequently used to map reference angles, the input, and their multiples, their coterminal angles, as well as angles on the axis, the quadrantal angles, to the values of sine and cosine. Okay, so let's start filling in our unit circle using this knowledge of reference angles. And I'm going to start with the degrees because I know that's probably what you're most comfortable with, but as soon as we start using our radians to connect to those reference angles, it's really important that you start working to get comfortable with radians as soon as possible. So zooming into this first quadrant, we know that this is 30 degrees, 45 degrees, and 60 degrees. Now 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. Now let's connect that pi over 6, pi over 4, and pi over 3 to some context. So we also know at 0 degrees and 0 radians, we have our initial side. When the initial side and the terminal side are at the same place, the positive x-axis, we have a radian and degree measure of 0. And this point happens, this point here on the unit circle has an x value. It is 1 unit away. It is the length of the radius away from the center of the circle. And it has a y value of 0. It has gone up none. If we go up to our 90 degree reference angle, we have a 90 degree reference angle. This is pi over 2. This is pi over 2. It's coordinate is 0. It is directly above the origin, so it has no x values, and it has a y value of 1. And our next quadrantal angle is another 90 degrees, so 180 degrees. This is pi. This is pi. Notice that if this whole side is 180 degrees, then that is equal to pi. Then this 90 degree section cuts 180 degrees in half. It also takes pi and cuts it in half. Pi times 1/2 is pi over 2. Notice if we cut this pi, this semicircle, into thirds, we get 1/3, 2/3, and 3/3. So our first pi over 3 is followed by a second 2 pi over 3. It is the second pi over 3. And 3 pi over 3 simplifies to pi. So that is why a 3 pi over 3 doesn't necessarily show up. But we can go another 60 degrees and see another pi over 3. If this was 3 pi over 3, if pi was 3 pi over 3, then this is 4 pi over 3. If we go another pi over 3, you guessed it, we're going to end up at 5 pi over 3. And it makes sense that one more pi over 3 would put us at 6 pi over 3, or 2 pi. And I'll write that in red like the rest of our quadrantal angles. 2 pi, and that is 360 degrees. So here's my first argument as to why radians are easier than the degrees. We get to count our way around the numerators rather than adding 60, adding 60, adding 60, adding 60. So we can write in our degree values for the pi over 3 reference angles. If we add 60 to 60, we get 120. 120 plus 60 gives us 180. 180 plus 60 gives us 240. Plus 60 gives us 300. And plus 60 puts us right back at 360 degrees. So our full circle to pi. Now let's do it with the pi over 4s. Pi over 4 is 45 degrees. So if I go 45 degrees more, I end up at 2 pi over 4, which simplifies to pi over 2. If I go 45 degrees more, I have 3 pi over 4. And how many degrees is that? Well, that's 90 plus 45. And we end up with 135 degrees. So notice the distance between these two skinny slices is 15 degrees. 120 plus 35 is 15 degrees. So big slices are 30 degrees, small slices are 15 on this unit circle model. All right, so we can keep counting. After 3 pi over 4, we get to 4 pi over 4. That's just pi. So there is 4 pi over 4. We go another pi over 4, and we end up halfway to the next quadrant. Through the next quadrant, and that is 5 pi over 4. Again, 45 degrees more, and we end up on the next quadrant. That's 6 pi over 4, or 3 pi over 2. And so we'll write that in red with our other quadrantal angles. 3 pi over 2. That's 6 pi over 4, simplifies to 3 pi over 2. And that's 90 degrees past 180. So that is our 270 degree mark. Now, between all of these, we've gotten all our quadrantal angles. All right, last pi over 4 takes me 45 degrees beyond 270, and that was 270 was 6 pi over 4, so this is 7 pi over 4. Then we're going to look at our degree value. There is 45 degrees more than 270. That is 315. Notice again, that's 15 degrees past 300 degrees. So the distance between those little slices. Another pi over 4 would take me to 8 pi over 4, which is 2 pi. Okay, so you always can think 2 pi in terms of pi over 4s. That's 8 pi over 4s. All right. let's think lastly about our pi over 6's. So if we split the top half, this semicircle, into 6 sections, we get 1, 2, 3, 4, 5 dividing lines. And those 6 sections are each of 30 degrees. So 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees, and another 30 degrees. All 6 of those 30 degrees add to 180. So we can count our way around the 30-degree sections. This is my first 30 degrees. And my second 30 degrees, 2 pi over 6, simplifies to pi over 3. Another 30 degrees is 3 pi over 6. That's pi over 2. Another is 4 pi over 6. That simplifies to 2 pi over 3. 5 pi over 6 lands on my next 30-degree mark. So that is 5 pi over 6. It doesn't simplify. There's our first new angle. Now 5 pi over 6 is 15 degrees past 135. So that is 150 degrees. And notice that's 30 degrees shy of 180. So my next pi over 6 lands at 6 pi over 6, just pi, 180. Then we go another pi over 6. That is 7 pi over 6. 7 pi over 6. And that is 30 degrees past 180, so that is 210 degrees. Oh, I forgot my degree value on 5 pi over 4. That's going to be 15 degrees more than 210, so that's 225. Again, I don't have any pi over 6's that are independent of the others. My 8 pi over 6 simplifies to 4 pi over 3. 9 pi over 6, 3 pi over 2. 10 pi over 6 simplifies to 5 pi over 3. And finally, 11 pi over 6 is my new one. So 11 pi over 6, that's just pi over 6 shy of 12 pi over 6, which would take me to 2 pi. So 15 degrees more than 315 is 330, and that's 30 degrees shy of 360. So there are where all of our angles come from and how we can build our way around this unit circle using reference angles. So notice that the reference angle, if I pick a particular angle, say we look at 5 pi over 3. My initial side is on the positive x-axis. My terminal side is 5 pi over 3. It traveled around 5 pi over 3 sections, 5 pi over 3 radians. That is 300 degrees. And so this represents a sketch of that angle 5 pi over 3. But its reference angle will be the angle between the terminal side and the nearest side of the x-axis. So here, our nearest side of the x-axis is the positive x-axis. So if we connect those with a line, this should make a right triangle. So the line we draw should always make a right triangle with the x-axis. And our reference angle is here. It is the angle between the positive x-axis and the terminal side. Here that happens to be pi over 3 away from 2 pi. So pi over 3, 5 pi over 3 is a singular pi over 3, or 60 degrees away from 360, or 2 pi. And so our reference angle there is 5 pi over 3. So notice, as we work through our coordinates, that angles with the same denominator all have the same reference angles. So all the pi over 3's will have a reference angle of some multiple of pi over 3. Here's pi over 3. Here's pi over 3. Here's pi over 3. And here's pi over 3. All the pi over 3's have a reference angle of pi over 3. And when we say reference angle, we're not necessarily talking about an angle in standard position. For example, this 4 pi over 3 angle, I connect the origin to my point on the unit circle, and I connect to the nearest x-axis. Notice I'm not connecting to the nearest y-axis. This is a no-no. Reference angles always land in the bow tie. The magical bow tie is what I like to call this. Reference angles always land in the bow tie. So one of the 4 triangles in this bow tie will be represented in or will match the triangle that you draw in orientation. So if you draw this triangle, you should say, oh, that doesn't look like it belongs on a bow tie. So if I am connecting this terminal side to the negative x-axis, I end up with this triangle, which is this triangle on the bow tie. Okay? So this 4 pi over 3 angle does have a reference angle of pi over 3. Now that's not an angle in standard position. Its initial side is on the negative x-axis, but a reference angle doesn't always happen in standard position. It's just helpful for us to know that all the reference angles, all the trig values and coordinates that happen at the same reference angles will have the same coordinates, x and y values, just with different signs. So let's start going through those. For the pi over 3's, we'll start there. We have this special right triangle, this 30, 60, 90. So the angle here is 60 degrees, the angle here is 30 degrees. So we know that from previous lessons that the short leg of a 30, 60, 90 with a hypotenuse of 1 is equal to 1/2. And the long leg is equal to the square root of 3 over 2. So if cosine is the x's and sines are the y's, then the x value here is 1/2, and the y value here is square root of 3 over 2. Notice that a very similar triangle can be used, and actually the exact same triangle can be used for our pi over 6 situation. So if I look at the triangle I create when I'm looking at my reference angle for pi over 6, the reference angle for pi over 6 does happen to also be pi over 6, that's 30 degrees. This is also a 30, 60, 90, but this time the x value is the long leg, and the y value is the short leg. So root of 3 over 2 is the x value, and 1/2 is the y value. So pi over 3's and pi over 6's have exactly flipped magnitudes. Our 45, 45, 90 triangle, and I will just draw this off to the side, we know that 45, 45, 90's have a really handy-dandy property, and that's the fact that they are always isosceles triangles. So 45, 45, 90's that have a hypotenuse of 1 have both legs equal to the square root of 2 over 2. So that will be the value of our pi over 4's, and I'll stick with my color code here. Square root of 2 over 2. All right, so if I go all the way around the circle, I can find all of my reference angles are going to have the same magnitude, just different signs. And so we talked about on Wednesday the signs of all the functions in each quadrant. And so cosine, if we remember, all students take calculus. We know all of the functions are positive there. That's why all of our coordinates are positive there. If students is in quadrant 2, I'm looking at students. That means sine, and its buddy cosecant. Sine of x and cosecant of x are positive. Everybody else is negative. That means cosine of x, secant of x, and cotangent of x and tangent of x. We also know in quadrant 3 that students take, so take, that is tangent and cotangent are positive. So negative is everybody else, sine, cosecant, cosine, and secant. Last one, calculus. All students take calculus in quadrant 4, IV. Roman numerals, V is 5, and a 1 next to it says subtract 1. So that is IV for quadrant 4. Here, cosine and its buddy secant are positive, so everybody else is negative. Tangent, cotangent, sine, and cosecant are all negative. So I listed all of them for some helpful reasons. That is because you will need to be able to identify whether any of them are positive or negative. Right now, we're just going to list sine, cosine, and tangent. And that reminds me, I should also list my tangent values in quadrant 1. So let's think about sine over cosine, or y over x. For my pi over 6's, tangent of pi over 6 will be equal to y over x, so 1/2 over root 3 over 2. Now when I'm dividing fractions, all I have to do is multiply by the reciprocal, so that is 1/2 times 2 over root 3. And that simplifies to just 1 over root 3, but we typically like to rationalize our answers. So if I multiply the top and bottom by root 3 over root 3, I'll have root 3 over 3. So the tangent here, tangent of pi over 6, and I'm not going to write the tangent of pi over 6 and the tangent of pi over 4. I'm just going to write them in orange. So tangent is 3 pi over 3. Now if I have root of 2 over root of 2, that is y over x, the tangent of pi over 4 will just be 1. Now the tangent of pi over 3, I'll also do off to the side, will be square root of 3 y over 2 y over x, 1/2. And so here we end up with the square root of 3 over 2 times 2 over 1. So the 2's simplify out, and it's just root of 3. So all the tangent of pi over 3 reference angles will be some sine of root 3. All right, so I know that all of my pi over 3's will be 1/2 root 3 over 2. And in quadrant 2, I know that sine is positive and everything else is negative. That means cosine is negative. So the pi over 3 in quadrant 3, tangent is positive, which means both of these are negative. So 1/2 is still my x, and square root of 3 over 2 is still my y. In quadrant 4, 1/2 square root of 3 over 2, and I know cosine is positive. That means everybody else is negative. That is, sine is negative. And square root of 3 is my tangent in all those 3 places. I know tangent is negative in quadrant 2, so this is negative square root of 3. Tangent is positive in quadrant 3, so positive square root of 3. And tangent is negative in quadrant 4, so negative square root of 3. Goes with all my pi over 3's. Finally, I get to keep doing square root of 2 over 2 for all of these. Because they all have a reference angle of pi over 4. And I just need to adjust their signs. So cosine is negative in quadrant 2, sine and cosine are negative in quadrant 3, and just sine is negative in quadrant 4. Last but not least, we need tangent on those. So tangent is still 1 in quadrant 2, but it will be negative 1 since tangent is negative there. Tangent is positive in quadrant 3, so we have 1, positive 1 again. And in quadrant 4, we have negative 1 again. Last, we have our pi 5 over 6's, so square root of 3 over 2, 1/2 turns into just negative square root of 3 over 2, 1/2 for negative cosine. Positives, both are negative in quadrant 3. And in quadrant 4, cosine is positive, but sine is negative. So the last things that are missing on my reference on my unit circle are the tangents for those. They're all going to be square root of 3 over 3's, and they'll be positive in quadrant 3 and quadrant 1, and negative in quadrant 2 and quadrant 4. So last thing is just the coordinates on those quadrantal angles for 180 degrees, or pi, and for 3 pi over 2 and 270 degrees. And I also want to list the tangents at those points. So here we have -1, 0. We go over -1. We go left 1 and up 0. And at 3 pi over 2, we have 0, -1. We don't go over any, but we go down 1. The tangent at 1, 0 will be the tangent of 0 degrees, or 0 radians. And that is, again, sine over cosine, so 0 over 1. That is equal to 0. The tangent at pi over 2 is 1 over 0. That does not exist. So tangent is undefined here. That happens at the other quadrantal angle 3 pi over 2. Tangent of 3 pi over 2 is negative 1 over 0. So that is undefined. But we do have a value of tangent at pi. That is tangent of pi. That's sine over cosine, or y over x. That's 0 over negative 1. That's just 0. So there you have your fully filled out unit circle. And I encourage you to make sure that you can do this on your own. See if you can walk through building every piece and part of it on a blank one all by yourself, okay? I really encourage you to make sure you are working with reference angles and with radians as much as possible. If you have to work in degrees, you can, but being able to work in all radians is absolutely a skill you need if you want to go to calculus next year. And it is something that will help you get up to the speeds that will be required to finish our assessments in a timely manner. So I'm going to leave these last problems to you as an exercise, and the answers will be posted. So please check those out.